The next section I'd like to consider is a practice with second order half-life. I'm not real fond of the way that I ended up having this typed, so I'm going to just cross this off in my notepad and just refer us to the way that I kind of have it better written on our formula page. The half-life for a second order reaction, and that's what T half means, is 1 over the K constant times the original concentration. Notice that I'm noticing here that the original concentration does play a role in second order half-life. It did not play an order up here with first order half-life. It was just simply knowing the K constant could get us there. So a little bit different formula. I like to see that as T1 half equals 1 over K times the original concentration. And what that means to me, and just kind of a side note, the lower the concentration of that original value, the greater the half-life. It takes longer to decompose. In contrast to behavior of first order reactions, the half-life for second order and other reactions depend on reactant concentrations. And therefore, it changes as the reaction proceeds. It's going to slow down. So therefore, it's a different value each time, whereas in the first order, it was a constant. In a zero order rate law, zero order, we understand that changing the concentration does not change the overall rate. That brings our attention to this area on our formula page, zero order, where A goes to B, but A has absolutely no effect. So look what happens. Rate is equal to K times the concentration of A raised to the 0 power. That's going to drop out. Rate is the rate constant. And what we notice then when we begin to integrate this rate law to get a straight line axis, it's simply a direct comparison to the concentration of A over time. No natural log, no reciprocal, but a direct correlation. K will end up to have a negative slope, so we put the negative in front of K to make sure we report K as a positive value. Our y equal mx plus b form says the concentration of A remaining at any point in time is equal to negative KT, that same point in time that went by, plus the original concentration. And we also can see on our formula page the half-life for a zero order, the original concentration set over 2 times the rate constant K, 1/2 the concentration that was original over the constant K. So we're just really looking at those formulas. So a zero order, the rate does not change with concentration. The integrated form says the concentration of A is directly equal to negative KT plus the concentration of A original value. And when A is exactly half the original value, we call that half-life. Just the definition of half-life. How long does it take for the original value to be exactly half gone? And what we saw there, and again from the formula page, no need to memorize, that the concentration of A, original value, set over 2, that's 1/2, that's a half-life, times K, the constant. These are not common. Zero order half-lives are not commonly calculated. Our text does mention them, so I will as well. A little bit of surface area chemistry when we're talking about enzyme chemistry or metal-based catalysis. It may play a role there, but again, not often appearing in an AP type problem. Friends, we are now finished with the lesson from section 14.5, looking at the integrated rate law. So temperature and rate is what's picking up. I'm sorry if I said this wrong. 14.4 has been completed. 14.5 picks up here. That tells me that I'm ready to assign you, and again for Tuesday over break, the third assignment. I have crossed off number 41, so if that looks like it's been crossed off of your notepad, it indeed has. This is the front maybe of what your notepad has. So 41 I crossed off. That gives us 33, 35, 36, 8, 9, 43. Solutions are also available on this website. So reminder, we've gone through the notes slowly and carefully, filled that notepad in together with the video lesson, and also assign is a lesson number 3. Good luck. Email me if you need to.